So, welcome to week 4. What we've done so far in the first 3 weeks is we've talked a lot about algorithms, we've talked a lot about science, we've talked a lot about the links between science and computer science, and we've talked a lot about how we can classify algorithms, analyze algorithms, and we've seen a menagerie of sort algorithms and their properties. And as I said at the time, the reason we were learning these wasn't to learn sort algorithms. It's interesting to know sort algorithms, sure, but in practice, if you needed a sort algorithm, what would you do? Steal someone else's. Yes, but how do we phrase that in scientific speech?
Implement.
Yeah.
Use an implementation you already have.
We would stand on the shoulders of some other great person. We would get a man to do it. We would go down to the shops and buy someone else's sort. I don't know how we'd phrase it, but you'd be mad to implement your own sort or your own version of these sorts, because what would you most likely do if you were going to implement one of these well-known sorts yourself?
Screw it up.
Screw it up. Who said that? Yeah. You said it? Yeah, that's what we'd do. We'd screw it up. It's just human nature. No matter how smart we think we are, we're wrong. We always make mistakes. So someone else has put hundreds of hours into testing and working it out. So for a standard solution to a standard problem like that, we'd probably use someone else's. So we're not studying sort algorithms for the point of studying sort algorithms. We're studying them, of knowing about. We're not studying sort algorithms because I want you to know how to write a million different sort algorithms. We're studying sort algorithms because I want you to know about algorithms, and they provide nice examples. And that leads me to the Google point, which I haven't said yet in the course, and I should say. Yeah, Adam.
Is that why all these libraries and things are like online, like LibXML and all that? Like
Yes, that's exactly right. That's why there are so many libraries written, and modern languages like Java, or even C, come with huge libraries you can use. The idea is, in computer science, we hate the idea of reinventing the wheel. Everything we do is riddled with errors. So what about if 100 people all put their effort into making one thing right, rather than 100 people making 100 copies of the same thing and getting them all wrong? So we work really hard as a community to get a few versions of everything right, and then we put them in a library, and then everyone else can use them. And then you can go on and do smart and amazing things to solve your problem, and your entire brain power is devoted to your particular problem, rather than the intricacies of how to implement sort. And let someone who spends their entire brain and lifetime thinking about sorts implement the sort. Because there's not because we let them do the fun part, though that is fun, but because there's heaps of other fun things we can do, and we want to just use their sort so we can get on with the things that we're really interested in doing. Now, so the Google point I wanted to make was this. I've noticed a few people have been working things out for themselves, and a few people sometimes have been Googling and just getting the answer. And I thought, how can I explain why I don't want you to do that? But I don't mind if you do that. It's not like high school anymore. You're not going to get in trouble if you do that. You can do whatever you want. But I'd like you to make the decision that you don't want to do it. So let me tell you the thoughts that go through my mind as to why I don't really want you to Google things. And I was thinking, as I was toying with how to explain it this morning, I was thinking, I saw this guy go past and he was very muscly. And I imagined that he goes to the gym and lifts up really heavy weights. And if you know how the whole thing works, you get really muscly if you lift up a weight that's heavier than your muscles can handle, so your muscles fail. And in failing, they record a message saying, must remember to get bigger tomorrow. And in a way, that's sort of how we want your computing to go. We want you to be pushed right to the limit, so you go home thinking, must practice that tonight. Okay? So now imagine that guy at the gym, and he's got a friend that goes to the gym with him. And his friend at the gym, to make it all simple, we'll call Jim. And he's showing Jim around the gym, and he's saying, and look, here is where you lift the weight. And if you lift this really, really, really heavy weight, which I've tried, I can lift 100 million tons. I can lift 100 kilograms. Or I have no idea. I'm out of my depth here. What's an impressive amount that a human being could lift?
100 kgs.
100 kilograms. Hey, I was right. I was spot on. Thank you. I like you. What's your name? So exactly, that's what I meant. 100 kilograms. Write that down. It could be in the exam. So this guy's going, I can lift 100. And he lifts 100. And then his friend, Jim, says, no worries. And he goes, I've got a friend with me here called Google. And he says, Google, lift 150. And Google comes along and goes, yeah, sure. And he goes, see, I can lift 150 and it didn't even hurt. The point of the whole exercise, oh, that's quite a nice phrase. The point of the whole exercise wasn't raising the weight off the ground. You could pay someone else to raise the weight off the ground, or you could use a lift or a lever. Or you could use hydraulic things or a pulley to get it off the ground. But the point wasn't raising the weight off the ground. What was the point?
Growing muscle.
Going through the process of lifting the thing off the ground. We didn't actually want the thing off the ground. That wasn't our objective. Our objective was to go through the process. So similarly, when I ask you to do something, I don't actually want you to do it. Does that make sense? I don't care what, I'm not saying that well. If I say, what's the biggest number that's a square number that's a palindrome? A square number that's a palindromic number. A number that goes, digits go in order one way and then reversed in the other, you know, like a palindrome. What's the biggest palindromic square, I don't know, which has less than 100 digits in it? If I ask that question, I don't really want to know what the biggest palindromic square is that has less than 100 digits in. If I did, I could Google it or go to Wolfram or something like that and look it up. I don't give a damn what it is. What I want you to do is... You cannot answer it. Out, get out, get out, get out, get out. Oh, no, or hang up. You have the option. Yeah. Now, your challenge is next time to turn it off or to have a better ringtone. Okay. No, ooh, what do you mean ooh? It's always safe to make fun of someone's ringtone because they're always crap, even the ones I pick. You personally love your own one, but everyone else just goes, what? So, gathering my thoughts again. Oh, did that sort of make sense? I think I finished the story. That we don't really care what the number is. I don't want you to tell me the number. My life isn't hanging on knowing the number. I want you to go through the process of finding the number. It's not the number that's important. It's the process you go through. How you do whatever you have to do that. That's what stretches you and strains you. So when I ask you to do something, you can always look up the answer on Google, but there's no point. I mean, there is a point if you want to sort of show off or say, hey, look, I can lift 150 or something, but there's no point in terms of you yourself changing, which is why you're at uni, presumably, because you haven't, you know, we want you to go through the process to change. I'm saying the same thing over and over again. You get the idea. Okay. Oh, and let me tell you about the fat man. Yeah, I used to always have this idea about the fat man, because whenever I had a technical problem, like I wanted to buy a certain microchip, and it was out of stock and I wanted another one and I wanted to know if one would work, or my washing machine broke and I wanted to fix it myself and they kept wanting to sell me $1 million part and I just needed to know if this diode was that or this. Whenever I had like an elaborate technical question, I'd always ring up customer support. Hello, hello, and they'd say, what's your name? And I go, and what's your address? What's the model of your machine? And then, what's your problem? I need to know if the diode is, you know, can I put a 20 volt diode in because I've only got a 20. They go, oh, hang on a second. Have you turned the washing machine on? No, I know why it's broken. I just need a diode. Have you tried, you know, turning it off, then turning it on? You know, no. And the person I'd be speaking to would always be an idiot, but I would know because they're going through a script to solve the problem. Not an idiot, but not a technical person. I wanted a technical person. I wanted to speak to the technical guy. And after a while, I realized what I had to do was say, is there just a really fat guy in a back room somewhere? And they'd say, yes, give me the phone, put him on the phone. And eventually, you'd go through enough people and then you get to the fat guy at the back and you'd ask the fat guy and he'd know the answer. And I think of Google as like the fat guy. And my thought in life, once I realized this one too many times after going to too many shops and eventually after lots of boring questions, have you turned it on and off? Yes! They'd go, I'll get Ralph, he might be able to help you. And they'll go out the back and they come back with the fat guy. After a while I realized that the fat guy was a guy that knew a lot of stuff. And he was an expert. He just knew information. But what was important to me wasn't knowing stuff, was being able to do stuff. So I formed this life-shattering breakthrough that I thought, I never want to be the fat guy. I just want him to be my friend. I want to know the fat guy. And that's why it's so good now that we have Google, because Google's everyone's fat guy. So none of us have to be the expert that knows stuff, because knowing information is irrelevant. Just knowing stuff is just not what life's about. It's what you can do with it. So Google knows stuff, but when I want you to work something out, sometimes I want you to go through that's a very long story to say that. Okay, so that's what we've done so far, with this sort of notion of science. And today we're finishing that off. And we're moving on to the next phase.
Google doesn't know everything, like, I mean,
sometimes Google doesn't know everything.
Well, you know, like, I mean, once I teach the fat guy the fat guy, once I actually teach him how to use Ping.
You had to teach a fat guy how to use Ping? Did you feel yourself putting on weight as you were doing it? You had to teach, okay, yeah, look, I'm being cruel. It's not always a fat guy. And fat guys don't always know everything. I don't want to stereotype. But that was just a breakthrough I had when I was 17, and I realized that. Okay. I was pretty fat too, actually, I must admit. Okay, guys, so what we've done so far is talk about science. I want to recap on it and summarize it, and then we're going to move on. The recap is this. We saw three things about science that I thought were interesting and worth talking about from the point of view of learning computer science. One was, I like the mechanics of doing science. I think they're admirable in many ways, and in many ways that's what computer science involves or should involve. And by the mechanic I mean the day-to-day stuff that you do, like the notion of being systematic, the notion of having a plan, and working to an explicit plan, the notion of recording what you do. If you've ever been attacked by a virus or your machine's been compromised in some way, and you try and fix the problem, I've discovered it's really important to have a notebook next to you and write down every single step you do, because 9 steps of the way through you'll suddenly realise, oh hang on, could it have reinfected at that stage when I rebooted and that thing was in that slot and I didn't have the right protect tab in, or did I have the right protect tab in at that stage? I can't remember. Well, now I always know because I've got a log of every single thing I've done while I'm fixing the problem. So, and scientists do that too. They keep a lab book. They keep a record of what they do. So I like this idea of recording what we do, of being systematic, of being methodological. How do you say that word? Methodical. Thank you. Methodical. Secondly, there were different notions of truth, like scientific truth and legal truth, and religious truth, and magical truth, and economic truth. And so in truth, we looked at this notion of, in science, we looked at this notion of how do we know when things are true, how do we know when things aren't true? And by the word know, I mean know as a scientist would say it, rather than as a philosopher would say it, or the man in the street would say it, or a newspaper reporter would say it. How do we know certain things? Like, for example, how do you know the Earth revolves around the sun rather than the sun revolving around the Earth? How do we know that? I mean, how do we know the Earth is spherical rather than flat? Well, you haven't observed it.
We went to the beach and saw the sails of the ship over the horizon.
But maybe that ship was slowly rising up out of the water. He's saying the sails over the horizon. I like that idea, that as it goes further away, the sail. But that could be something to do with light bending or something. But yeah, that's good evidence. But how do we know these things? How do we know that objects fall at the same rate regardless of their mass, in lieu of all other things, and so on and so on and so on? How do we know these things? What is it that gives us confidence to say that's right or that's wrong? And the last idea that we got from science was this notion of abstraction. And abstraction was the idea of, do you remember what did we say abstraction was? Yeah, what is it though?
It's like we've got like say some stuff here, like for instance the good like Windows or something, like you're just using your computer with Windows on all, you're not seeing what's behind it, like what it's doing. Like,
yes, that's an example of being abstract. Can we generalize that though? Can someone?
I'm sort of not sure how to generalize it.
But that's a perfect example. The idea of you could use Windows and not sure what's going on under the hood, but you can still use it successfully and do things. Can someone come up with a general...
interface for any sort of kind?
Look, that's getting close. An interface of some sort, yeah.
Paying attention only to the important bits.
Paying attention only to the important bits. Same thing. Yeah, yeah. The idea of abstraction is we don't worry about what a thing is, we worry about the attributes of a thing. And the attributes are normally things we can measure. Being abstract in different ways is you pay attention to different amounts of things or different... So I could only care about your weights if we were wondering about... There's a bit of a weight theme today, isn't it? I'd only worry about your weights, the weight of a student. I could abstract all your other properties away, whether you're happy or sad, whether you're going to be this or that, so whether you're, whether it's your birthday today. All those things I could throw away. If I was designing this hall and had to build the seats so the hall was safe, maybe all I care about is your mass and general density. Maybe that's all I care about. So abstraction is, we don't care about the thing as a thing, we care about the thing in terms of its attributes, and sometimes we don't look at all the attributes. And when we don't look at all the attributes, that gives us interesting classification things, and we talked about that. All right, so they're the 3 steps. Do you remember that? The 3 bits of science. The mechanics of science, notions of truth in science, and abstraction in science. And now we're going to go through each of those things and apply them to something. So the mechanics. First of all, I'm hoping that task 2, guys, shh. This is the talky corner, isn't it? You guys are talky. Is it just one person? I bet it is. I bet there's one person here who's some sort of... I bet they're on that side and they're a ventriloquist and they're trying to get you guys in trouble. All right, so shh. If you work out who it is that's talking, just surreptitiously let me know. Okay. Yeah, to me, I'm talking. So what was I saying? Because it throws me off when I rouse on people for talking, you see. I guess I could just not rouse on people. I can't remember what I was saying. But so there's this, the thing I really like about the task you're doing at the moment, task 1, is it's requiring you hopefully to go through the scientific process. It's requiring you to, not knowing the answer, try and work out some stuff. And I'm trying to put you in the same position as the astronomers were 100 years ago, when they didn't know how the universe was constructed and they were looking out there and they're having theories. You're trying to classify some sorts. You don't know how I've implemented them. You've got some theories, some clues from things I've said, some ideas about what's reasonable and not. You're forming models, and then presumably you're running tests on your models and you're trying to work it out. But the annoying thing is, there's no Google you can look up, is it? I mean, in the old days, the astronomers, when they wanted to work out, I don't know, if the Earth travelled in a circle or an ellipse, they couldn't just look it up on Google because no one knew the answer. They had to work it out. It was new information. And this is, of course, why we want you to go through the process of learning how to work out information. So when you get to the boundaries of what we know, you can keep going. So vintage Google. Vintage Google was probably called the Bible or something like that. Yeah. Let's just look it up and see. No, the Earth goes round, the sun goes around the Earth. Certainly, I'm sure Copernicus and Galileo and all those guys got in a lot of trouble with the established church at the time for their crazy theories. So, in this assignment, you've got the same position that you don't really know what's going on. You won't even know when you've got it correct. You'll have no certainty. There'll be no closure. You'll hate this if you normally just do maths and like tick the answer and move on. Because you won't even know if you're 100% right, will you? You'll always have a nagging doubt. And that's sort of how science goes. You just do the best you can. So let me warn you not to burn yourselves out and kill yourself. I don't want you to think, oh, I have to get everything 100% perfect in this assignment or I can't finish. Because I don't think you can get it 100% perfect. It's just not possible. But I imagine everyone will, with a bit of effort, should be able to get most of the marks. But don't keep going until you've got absolute certainty, because you can never have certainty with new knowledge, only with existing things we know. And this is new, because I've deliberately kept information away from you. Okay, now, do you remember, also in science they do experiments all the time to get information rather than just making it up out of their head. A couple of days ago, we did an experiment in class. Do you remember what it was? I've highlighted it to sort of help you. No, I haven't. I've highlighted the thing above it to sort of help you. What was I doing? Remember we were doing an actual experiment to work something out. The birthday. I was trying to work out what's the likelihood, if we go through asking people when their birthday was, how many people are we going to have to ask before we come across someone with a birthday which is the same as someone we've already asked? That didn't make sense? I'll say it in French. Le birthday asking. I'll say it in English in different words. How many people do we have to ask in the following scenario? Scenario is this. Richard will ask everyone what their birth date is, ignoring the year. Everyone will loudly say it so that everyone can hear. At some point, someone will call out a birthday that has already been said, at which time we can stop. And my question was, how many do we have to ask? And I wanted to show you that the number you have to ask is related to the square root of the number of days in the year rather than the number of the days in the year. Or in other words, the number of possible matches grows quadratically, is a square. Yeah, the number of possible matches is NC2, it's n squared. So every time we ask someone else, we get n more possible matches, not just one. So the number of possible matches is growing quadratically. And that was definitely deliberate. And is growing quadratically, so the chances of it working quite soon are much higher than you would expect. And I talked about how maths teachers like to do this, blah, 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 blah. And then to prove that we'll probably get a match really soon, because the expected value is 20 or 24 or 27 or something, I went round and we must have done about 50 people. And unless you were lying or no one was listening for a match or something, we actually got through an enormous number of people and didn't find a match. And I thought, oh, that was a bad experiment. It took a really long time to do. It failed, and it didn't demonstrate the point I wanted to demonstrate. So as an educator, I went home and smiled. I thought, wow, it's very rare that 3 things simultaneously go wrong. I need a trophy for that. So if I was a real scientist, though, what would I do? And this was a real lab. I've done one experiment about the expected value of something. It didn't work. What should I do? Do it again, and do it again, and do it again. And that costs lots of money. So that's why science costs lots of money lots of times. You have to repeat your experiments over and over again. How long would it take? It would take up all the lectures. I thought what we could do is the first 10 minutes of every lecture I could go around asking that question again. And we could record how many it took every lecture, and over the 50 lectures in the course or 40 lectures in the course or however many it is, we'd have another 30 samples or something. We'd use up hours and hours and hours doing it, but we'd start to get an average. And then I thought, no, hang on, I know a better way, which is theory. No, it's experiment. I want to validate the theory. I want to demonstrate it. I don't want to have concrete, strong, I don't want to have strong reasons why the result will be something. I actually want to show that the result appears to be something. I can tell the computer to do it, because the computer doesn't take as long as I did. And if you get the computer to do it 2 or 3 times, it doesn't mind. It doesn't get bored. So I wrote a program to do it. So this is an example of an experiment. Let me show you. Oh, the experiment. I wrote a program to generate birthdays at random. And add birthdays to a list one at a time. And every time we add someone, we check against everyone already in the list. And we stop as soon as we hit a match, and we count how long it took to get a match, how many turns it took to get a match. And then we recorded that, and then we repeated the experiment. It's not quite as graphic as I thought it would be. Let me just try and fix that up. Oh, my computer's frozen. Oh, no, it's worked now. It's worked. Did something happen? Oh, yeah, that looks good. Yeah, we're in. Okay, so here's my program. It's just called birthday.c. Can you see it? La 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 la, la 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 la. Some hash defines at the top. The number of possible birthdays. So suppose there's 365 birthdays. Let's do it 100 times. All right, let's go. Build it, go, run. Let's look at the console, the output. And it ran. Oh, let's go again. It just zooped through everyone. It asked, there's 100 trials here. You can see each trial. I asked 12 students this trial. I asked 37 students this time. I asked 29 students this time. And down the end, it says, on average, how many students I asked was 24.49. Woohoo! So that's about what I thought it would be, roughly. And I did 100 trials. So are we convinced? Well, I thought, I sort of want to know. Yeah, I want to know that it's not just lucky. I mean, I get the central limit theorem helping me here, but we don't know much about the underlying distribution, so we can't rely on that too much. So how do I get it back? Come to me, little window. So let's do it again. And this time, let's change the number of trials to be, I'm trying to get the 2 windows on the screen at the same time.
Yeah, see, if you had windows, you could do it pretty well.
Yeah, if I had windows, I'd do it really well. But you know that blue screen we got at the beginning when the projector was changing over? Apparently, Microsoft has registered that as a like a business trademark. That colour blue, like you know, Cadbury's registered the colour purple. Yeah, that's actually Microsoft. Yeah, it's amazing. Okay, here we go. So we're going to change the number of trials. Let's do it 1,000 times. 1 million? Oh, I like the way you think. Is that 1 million? That's 1 million. Off we go. Oh, it's going to print a lot. It's going to take a lot of printing. It's going to have to print 1 million things. I'm going to have to comment out the prints. Yes, I think that's what I'm going to do. Students this trial. There we are. Stop. Go again. Zoom. Ask 1 million of them. Ba-bum! It ran 1 million trials. On average, it had to ask 24.622. 662. 24 of them. Okay. So, that's the number I was hoping we were going to get with our first trial. But I was actually trying to convince you that this grew as the square in proportion to the square root of n. So what was n in this case? What's the number of possible birthdays? 365. So with 365 we get 24 or 24.6. To do a proper experiment now I'm going to vary the number of birthdays. So I could go, oh I don't know, what if there was only 100 and, what's half of 365? 182 birthdays in the year. And let's not do 1 million because that just took too long. All right, with 182 it took 17.5, 17.6 trials. So I halved the number of trials, but the expected time it took didn't go down by 2. Maybe it went down by the square root of 2. Can anyone work out what the square root of 2 is? What's this number times 1.4? What's 17.6 times 1.4? Doesn't someone have a calculator? Doesn't someone know the answer? Let's ask Google. What's that? I got a calc on the Mac. Oh, this Mac is there nothing it can't do. Let's find out. Calculator. 24.5, did someone say? That sounds too good to be true. So the square root of 2, it's 1. I think I have to change what sort of calculator it is. Let's have a look. I want a scientific calculator, please. It is a scientific calculator. Number of decimal places. I'll have 10 decimal places, please. All right. Times 24. Sorry, I went the wrong way. Times 17.6 equals times square root of 2, stupid Mac, is 24.89, approximately right. So I doubled it. If I ran time backwards, I doubled the size of the sample, but the amount of work it did only went up by the square root of 2. That's an indication it might be quadratic. So but am I going to stop at that? No, I'll try it again. I'll say, oh, well, I'll double it again. So 182 gives 365, gives 730. Is that right? Let's go, 730. Boom. The answer was 34.5. So let's get that number again that we had before. Let's clear that. And we had 24.6 times 2 square root equals 34.7. It's getting close. I mean, there's overheads. It's not exact. Remember, big O x squared doesn't mean it's exactly x squared. There can be constants and things floating around and lower order terms that'll interfere with small values of n. But once n started getting really big, it's only in hundreds now. Once I move it into the thousands or even more, and I'll have to increase the number of tests then to get statistically meaningful results. But as I increase the number of tests, I won't have to increase the number of tests. I'll just get bigger answers, won't I? Yeah, so I can keep the number of tests the same. As I get n really big, that'll converge, I assume, to the square root of 2 over time. That'll be the limit of the whole thing. Now, why did I do that? Because I didn't want to reason about it, because reasoning can sometimes be wrong. Though, of course, we always need reasons at the end to work out what's going on. But I was doing an experiment to gather information. It's too time-consuming to do a real experiment. That's why poor physicists and med people are just, looking not happy when you see them. I know a med researcher. She does these experiments. Each experiment costs something like $20,000 to run. If they're halfway through an experiment and they realise they've made a mistake, it's like, oh, I left the door open, or whatever. Oh, well, I'll just burn that $20,000 and haven't paid enough. But with computing, it's not like that at all. How easy is it to run experiments? So there's no excuse for not running an experiment all the time on computing. Whenever you have something you want to know about, don't just think, oh, I wonder. Think, oh, well, I'll have a look.
What if you're trying to experiment with the hardware and you're trying to experiment with like a cray and it sort of blows up or something?
Well, look, I think if you cause things to blow up, that's always a good thing. That's an interesting thing. Life's more interesting with things blowing up than not. But no, I'm not suggesting all problems can be solved by experimentation. But I'm saying if you have a problem that can be solved by experimentation, well then we're very fortunate, because in computing, experimentation is very easy. Okay, so going back to the lecture. Boom. I just was trying to show, what was I trying to show? Here we are. Oh yeah. We have more in common with science than we might initially think, because we are able to carry out experiments as well. Then that reminded me of a little puzzle. So you're all looking a bit sleepy. I might wake you up with this puzzle. This is from a famous mathematician. Some of you might know the answer already. Don't show off by calling it out. Just automatically give yourself a tick for knowing the answer already, and you're very smart. But don't spoil it for other people who have to work it out. Don't be a Google. Oh wow, so it's like an insult to be a Google.
You said Google was the fat man.
Google's a fat man. Oh, yeah, Google's so many things, aren't they? They're different things to different people. So yeah, so that's a phrase I think we should work into conversation more often. Don't be a Google now. We have a party. 5 couples go to the party. I go with my wife. Oh, I was about to cast myself in the role of the great mathematician. A great mathematician goes with his wife, the guy that invented the puzzle, and 4 other couples go. At the party, various people shake hands with other people because it's that sort of party. And interestingly, no one shakes hands with themselves. As a computer scientist, we're interested in that, and we check that out. And no one ever shakes hands with their wife because I don't know why you don't do that. So So anyway, people are shaking hands different numbers of times. What's the most number of times someone at the party could shake hands? 8. Assuming you never shake hands with someone twice. 8. Yeah, if you shake hands with each one in the other 4 couples. What's the smallest number of times you could shake hands? 0, yeah. So what the mathematician noticed was, bizarrely enough, the number of times everyone shook hands was different. It had all the possible values between 0 and 8 as he looked around the room at everyone else, not including himself, but everyone else including his wife. There were 9 people not including him, and the values 0 to 8, there's 9 of those values. So everyone shook hands a different number of times. And the puzzle is this. What you have to work out is, with that information, how many times did the man's wife shake hands? Does that make... No, you've got to work it out not because of politeness, no, using logic. Not because they're hosting the party, she'll have shaken hands with everyone. I like what you're thinking. No, using mathematics or using computing, using your brain, work it out. Using computing, you can do it with brute force. Using maths, you can do it with reasoning. I'd go for the reasoning. Okay, I was going to tell you about birthday tax, but I'm not going to now, because I want to quickly go down and talk about notions of truth. I was saying that science has a different notion of truth to other disciplines. Let me now make that really precise. In science, someone makes a claim, and after a while, scientists generally regard that claim as true, and it becomes called a law, someone's law. Yeah, Ralph's law, something like that. Murphy's law. No. Newton's 3 laws of motions. The 3 laws of thermodynamics. So on and so on. In the same way, and it's quite hard for a scientist to ever say something's right and to make it a law. And notice this, just because something's made a law, does that mean it's true? No, because there'll be a paradigm shift in the next generation or 2 of scientists, and suddenly everything we've known up until now is wrong. So laws don't actually mean they're right, they're just our best guess. Like Newton's laws of motion turned out not to be right. But we still call them Newton's laws of motion, because they work well at sublight speeds, for all intents and purposes. All right, so the last time I was teaching this course, a very keen student sent me a lab exercise and said, I notice you're teaching binary search in this course, and you always put the labs out late. Here's one you can use, so maybe you'll get them out on time for once. I said, oh, thank you. So here's the code they sent me. I'll make it a bit smaller. Can you see that? Can you read that, or is that too small? Might be too small. Let me see if there's a happy medium. No, there's not going to be a happy medium. I'm going to have to make it smaller. Okay, so this is binary search. Now you remember how binary search works. I've got, what have I got? I've got...
Leaves on a tree?
Got leaves on a tree? No, I don't have leaves on a tree. I've got spurs that jingle, jangle, jingle. No, I've got a collection of DVDs sorted by by barcode number. And I want to know if I have a particular barcode CD in that collection or not. Maybe I've got 10,000, did I say CDs or DVDs? I've got 10,000 DVDs. Would be nice. And I have a barcode, and I want to know if that barcode occurs in the collection. The collection's sorted by barcode. Well, binary search goes like this. Instead of moving along saying, is it the first one? No. Is it the next one? No. Is it the next one? No. And stopping as soon as I get to a value that's bigger than the value I'm looking for, because I know I can give up early then. So on average, how much work would I do that way? N on 2, because on average it'll be halfway through, I can give up. If it's not in there. No, if it's not in there, it'll take N on 2 on average. Yeah. And if it is in there, it'll take N on 2 on average. So it's N on 2 both ways. But binary search works like this. You pick the number in the middle of the range. Not the number in the middle, you pick the DVD in the middle. And you look to see if its serial number is bigger or smaller than your serial number. And if it's bigger than the serial number you're looking for, you throw away all the DVDs on the big side and you look on the lower half. So you've thrown away half the DVDs in one swoop. And if it's smaller than the number you're looking for, then you throw away all the smaller DVDs and you can only look in the upper range and you've thrown away half. And then you repeat that process, picking the midway point, the midway point, the midway point, the midway point. So every time you do a comparison, you can throw away half the things you're looking for, and at the end, how many do you find? How many comparisons have you had to done to find the thing you want? Log n in the worst case, isn't it? Log n. Okay, because you halve every time. Log to the base 2 of n. So that's binary search. And I'm about to teach it. In fact, I will be teaching it next week. So, in fact, it probably comes up in your labs this week. So, someone gave me some code and gave me a question using the code. Now, the very first thing I did as soon as I saw it was have a heart attack and writhe around on the floor, because that's what computer scientists do whenever they see an implementation of binary search. Because what do we know about any implementation of binary search that anyone has ever written ever? It's wrong. Binary search is such a simple idea, you'd think it would be hard to get wrong, but actually, it's generally wrong when people implement it. And can I be precise? Someone, it might have been Sedgwick, I'll find it and put a link up, surveyed computer science textbooks that taught binary search. Most of them had an incorrect binary search in there. Binary searches in standard libraries issued with software languages or with operating systems have incorrect binary search coded in them. A brilliant computer programmer once demonstrated by proof in his algorithms course that all the binary search algorithms in all the textbooks the students had was wrong, and he gave them a correct implementation. And 10 years later, he realized to his embarrassment that his implementation was wrong. It's a very simple idea, a binary search, but it's very easy to get wrong. It's not that binary search, by the way, is different to any other problem in computing. It's very easy to get everything wrong. We get things wrong all the time. The problem with binary search is it's so deceptively simple that well, you tell me, why do we get it wrong?